Section 5.3, the fundamental theorem of calculus. If f is the function whose graph is shown in the figure, and g of x is the integral of f of t dt from 0 to x, let's find the values of g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5. Then we'll sketch a rough graph of g. So first, g of 0. Well, that's going to be the integral from 0 to 0, because in this case, the function is of x, and x is the upper limit. So we don't plug into t, we plug only into the limit, and inside stays f of t dt. Well, any integral that has the same upper and lower limit is 0, because there's a width of 0 for any rectangle. So that g of 0 just becomes 0. G of 1, on the other hand, is the integral from 0 to 1 of f of t dt. So for that, we have to look at our graph. We see that we are going from 0 to 1. So that is going to be the area underneath this curve. So it's a triangle. So we're just looking for this area. So it's half of base times height. So for that triangle, it's going to be half of the base, 1, times the height, 2. So it's just 1. Let's get the next one now. For g of 2, that's going to be the integral from 0 to 2 of f of t dt. So that's going to be from 0 to 2, so it's this entire area that we're looking for. However, I already know that the area from 0 to 1 is 1, so all I have to do is get this area over here and then add it to my previous area. So let's do that. We'll get the integral from 0 to 1 of f of t dt plus the integral from 1 to 2 of f of t dt. So that's 1, because that's what g of 1 was, plus the area of this rectangle is 1 times 2, so that's 3. Next up, g of 3 is the integral from 0 to 3 of f of t dt. So that's just g of 2, the previous integral we got, plus the new part of the area that we haven't calculated yet, which is from 2 to 3. So that's this entire area we already have. We know that that equals 3. So we just have to get this new piece over here. Well, it looks like it's a little bit more than the triangle would be. The triangle would be 1 by 2, so that would have an area of 1. So we could say that the area of this entire thing is probably a little more than 1. How about 1.3? So let's say that this is approximately 3 from before, plus the new area, 1.3, which is equal to 4.3. Next up, g of 4. That's the integral from 0 to 4 of f of t dt, which is just g of 3 plus the integral from 3 to 4. So we said g of 3 was about 4.3. From 3 to 4, we have to get this area. However, it's underneath the x-axis, so we have to represent that using a negative number. If we said that this area over here was 1.3, this area under here is symmetrical, so it should also be 1.3. So we should subtract 1.3, or add negative 1.3, and get 3. Last but not least, g of 5. Well, that's just going to be g of 4 plus the new part. So that's from the integral from 4 to 5 of f t dt, which is about 3 plus negative 1.3 again, because that's this part. And that's 1.7. Let's try graphing this thing now. So let's say here's 1, 2, 3, 4, 5. And here's 1, 2, 3, 4. I don't think we have to go past 4, it looks like. So we start at 0 because g of 0 was 0. Then g of 1 equals 1. Then g of 2 equals 3. G of 3 was about 4.3, so we did have to go a little bit past 4. And then we went back down to 3. And then g of 5 was about 1.7. So we get a nice curve like this. Okay, we could say that we're done at this point. However, what's interesting here is that this is a maximum value. So the slope of the tangent line over here is 0. If I look over here, the value of this function at that value, at that x value of 3, is also 0. So if I also look along the interval from 0 to 3, I could see this thing's going up. And this function is positive over there. If I look over here, I can see the function is going down, and this function is negative over there. So it almost looks like f of t is the derivative of this function g, because it matches all those characteristics. That would mean that if I took the derivative of g, which is the derivative of the integral, my hypothesis is that I get back to f. Turns out that that's actually true in most cases, in some cases, depending on certain criteria being met. If our function is continuous in the closed interval, then we define the function to be equal to an integral, then the derivative of that function, the derivative of the integral, is equal to the original function evaluated at the endpoint. Let's try proving this. If x and x plus h are in the interval a, b, then let's see if we can figure out what the derivative would be. Well, we know the derivative is, by definition, g of x plus h minus g of x over h, and then we take the limit. So let's look at just g of x plus h minus g of x first. By definition, those are the integrals of f from a to x plus h and from a to x. So we know that we can split an integral, right? We can stop in the middle somewhere. So let's stop at x and continue from x. So if we go from a to x and then x to x plus h, that's the same thing as if we just went straight to x plus h. So we can rewrite this integral as the sum of these two integrals. But then we have minus a to x and plus a to x, so those cancel, and we just have the integral from x to x plus h of f of t dt. This means that if we divide by h, we get the integral from x to x plus h times 1 over h. So all we have to do is somehow take this limit. Well, it's not the easiest thing to do in the world, but it's totally doable. We know that f is continuous on the interval from x to x plus h if h is just some positive number. So since this is a closed interval, the extreme value theorem guarantees that there's a maximum and a minimum. So there's some x value u and some x value v, where the y values at u and the y values at v give a minimum and a maximum. If we take a look at it, we can even see that from the figure. We've got this closed interval from x to x plus h. Somewhere inside the closed interval, it could be at an endpoint, like over here, the maximum in this particular picture, or it could be farther along. Let's say this thing went down. Somewhere there's going to be a maximum, somewhere there's going to be a minimum. So we take this minimum value, we multiply by the length of the interval. The interval goes from x to x plus h. So that means that the difference b minus a is x plus h minus x. So that's just h. And that gives a lower estimate for the integral, as we saw in the previous section. We do the same thing on the other side. We get an upper estimate, the maximum times b minus a for the interval. So that means the value of the integral, whatever it is, must be between these values. I need it to look like this integral, though, with the 1 over h. So I replace m with f of u, because that's exactly what m is, and I divide by h. Now I have this integral in the inside, which is equal to this, so I replace it. So I know now that basically the derivative without the limit is less than or equal to f of u, which is less than or equal to f of v, where those are the minimum and maximum on the interval. If h is a negative number, then I can prove this pretty much the exact same way. So if h is negative, that means that the interval, instead of going from x to x plus h, it goes to x plus h to x, because h is negative, so x plus h is smaller than x. Well, then I just multiply by the length of that interval, which is x minus x plus h, so it becomes m times minus h, being less than or equal to the integral from x plus h to x of f of t dt. However, what I can do is I can flip this and put a minus, and that way I have the exact same integral as before. And then I can divide by minus h, and I get right back over here. Notice that dividing by minus h cancels out this negative, and it doesn't flip the inequality because minus h is a positive number, because we're assuming h is negative in this case. So it doesn't matter if you take h to be positive or you take h to be negative, you still get the exact same inequality in the end. Since we get the exact same inequality, let's let h tend to 0. In other words, let's take the limit now. So if we take the limit as h goes to 0, then that means that u approaches x and v approaches x. The x values where the minimum and maximum occur. This should make sense because what we basically do is we're sending this h value to 0. That's moving the end of the interval closer to the beginning of the interval. So I keep getting closer and closer and closer, but I still have to have a maximum and a minimum value inside this little tiny interval by the extreme value theorem, no matter how close it is. So there still must be a u and v in here somewhere as I get closer and closer to an interval that has no width, basically. So that means that those get closer and closer to the beginning also. They get closer and closer to x, both of them. Therefore, because this is a continuous function, the limit as h goes to 0, which is going to be the limit as u goes to x of f of u, will have to equal the value of the function f of x in either case. So that means that when I take the limit, I get f of x on the left and f of x on the right. So now I can use the squeeze theorem to say that the limit in between must also be f of x, because I get the same limit on the left and the right. So that means that this limit must be equal to f of x, but that limit is exactly what the derivative is. So that's proving that the derivative is the value of the function. So that means that, again, if I have an integral, assuming that the integral of the function is continuous on the closed interval, then the derivative of that integral, g prime, is the original function. It cancels out the integral, basically. You just have to evaluate it at your upper limit. Let's do an example of that. Let's find the derivative of the function g of x equals square root 1 plus t squared dt from 0 to x. Well, in this case, the function f of t is just the square root of 1 plus t squared. So that's a continuous function. Because it's continuous, I can apply the fundamental theorem of calculus. Part 1. So the fundamental theorem of calculus part 1 will imply that the derivative of this integral is the original function. So the derivative is just square root of 1 plus x squared. I just replace the t with the upper limit. And that's it. let's find the derivative of the Fresnel function. S of x equals the integral of sine pi t squared over 2 from 0 to x. And let's compare its graph with that of S of x. So by the fundamental theorem of calculus, because sine is a continuous function, we take the derivative of s and we get back to just sine. We cancel out our integral. So it's pi times x squared over 2. We just replace t with x. Let's pull out our handy dandy calculator emulator. Go to y equals. Go to math. Get number 9 as our integral. We'll go from 0 to x. And then inside we put sine. Let's see, where's pi? There it is. Pi, and we need to put t. So let's go to alpha 4 for t. We'll square it and divide by 2. Okay, close parentheses. And we're going with respect to t. And we'll graph, well, let's also graph the derivative. Almost forgot. So sine of pi x squared over 2. Looks cool, but it's kind of hard to see, so let's try zooming in a little bit. Okay, notice that blue is our integral function, our function s. Red is our derivative. Let's grab a picture of that. Notice that from here to here, our original function is increasing, and our derivative is positive over there. Then we hit a maximum value, and our derivative is 0. Then our function starts decreasing, and our derivative is negative over there. Then we start increasing again, and our derivative is positive, and then we just start decreasing right at the end, and our derivative becomes negative. So it really looks like sine of pi x squared over 2 really is the derivative of this integral of sine of pi t squared over 2. Especially when we look at the area underneath sine, it looks like that area is positive, and this function goes up. But then the area goes and becomes negative, and the function goes down, and then goes up. Let's find the derivative of secant from 1 to x squared. Notice this time it's not an x, it's an x to the 4th. Sorry, I said squared, but I meant 4th. So what we have to do is we have to somehow apply the fundamental theorem of calculus, but to something that's not x, to a function of x. Well, this should sound familiar when you're trying to do a derivative, but you don't have x, you have a function instead. Use the chain rule. So let's let u equal x to the 4th. Then the derivative of the integral from 1 to x to the 4th of secant t dt is the derivative from 1 to u of secant t dt. Well, by the chain rule, that's just the derivative, pretending that this was an x. So we just differentiate secant t dt, and then we multiply by the derivative. Well, this derivative is easy enough. That's just the fundamental theorem of calculus applied to that. Secant is continuous, so it's not a problem. So the derivative will just be secant u. Then the derivative of u is what we have to remember. Well, u was x to the 4th. So when we take the derivative of u, that'll just be the derivative of x to the 4th, which is 4x cubed. So when you apply the fundamental theorem of calculus to something with a function of x, you just keep the exact same thing and don't forget to multiply by the derivative of that function. For the fundamental theorem of calculus part 2, we say again, f is continuous on the closed interval ab, then the integral is equal to the difference in the antiderivatives at the endpoints. So here's an antiderivative at b minus an antiderivative at a. The fundamental theorem of calculus part 2 says we can choose this capital F to be any antiderivative, any function whose derivative is f. So to prove this, let g be this integral from part 1. Then the derivative is just f of x. You just take t and plug in x. So g is an antiderivative of f, because the derivative of g is f. So this g is basically a capital F. We proved in the past that if you have any other antiderivative of f on the interval, then it must differ by a constant, because when you take this derivative, you just get g prime, and then this is 0. So this is true for any x in the interval from a to b, so that means by continuity it's true in the closed interval. So we can apply part 1 again, and we see that g of a will just be 0, because that's the integral from a to a when we plug in x equals a. Therefore, f of b minus f of a is equal to, let's see, capital F of b, you just plug in b over here, so we get this g of b plus some constant, minus g of a plus a constant by plugging in a over here. The constant minus the constant cancels. G of a we just said was 0, so this whole mess is 0. So f of b minus f of a is just g of b. But g of b is if you take x and you plug in b. So that's this integral from a to b of f of t dt. Since it makes no difference between calling tx or tt, we basically have this now proven by part 1. So that's pretty cool. It means that we have a major shortcut for evaluating definite integrals. Before, our only shortcut was to take areas, otherwise we had to do an entire limit of a Riemann sum. But now we can just take any antiderivative, and just plug in our endpoints and subtract. Let's evaluate the integral e to the x dx from 1 to 3. We know that f of x equals e to the x is continuous. And we also know that the antiderivative of e to the x, capital F, is equal to e to the x, because the derivative of e to the x is e to the x. So this means we can apply the fundamental theorem of calculus part 2. So that will imply that the integral from 1 to 3 of e to the x dx is just capital F of 3 minus capital F of 1, which is e cubed minus e. We did this in example 3 in the previous section, and it was much harder. We had to use a calculator to do it, a computer algebra system, because it was so difficult to evaluate that limit. But now we can do it in 2 seconds. Notice that we can use any antiderivative. So that's why we decided to make c equals 0, because we could have made c equals 7, but then the 7 and the minus 7 would cancel anyway, so why make it any constant other than 0 when you can just make it easier? We often use this notation, a bracket from a to b, to denote this in shorthand. So that allows us to rewrite our fundamental theorem in a much shorter form. We can just say that the integral is equal to f from b to a, where capital F, when you take the derivative, is f. So f is an antiderivative of f. We also use sometimes just a vertical line without the bracket. I actually use that a lot. We also sometimes use brackets on both sides. I use that when it's a little bit confusing sometimes where the function ends. Let's find the area under the parabola y equals x squared from 0 to 1. So if f of x is x squared, then capital F of x is 1/3 x cubed, right? The power rule in reverse. You raise the exponent, divide by what you raise by. So now we have an antiderivative, we have a continuous function. We can take the area by the fundamental theorem of calculus part 2. So it's just going to be the antiderivative of x squared, which is x cubed over 3, evaluated from 0 to 1. Well, that's 1 cubed over 3 minus 0 cubed over 3, which is 1/3. We did this in the first section of this chapter. It was example number 2, and it took forever because we had to find the limit of a Riemann sum. But now we can just do it in 2 seconds. This integral is actually just shorthand. It's a lazy way of writing the integral from 3 to 6 of 1 over x dx. Sometimes we just put the dx in the numerator to save space. So again, we can use fundamental theorem of calculus. If f of x is 1 over x, then capital F of x is ln of absolute value of x. So if x is from 3 to 6, that means that capital F is equal to ln x, because we don't need the absolute value if we're just from 3 to 6. So our integral becomes 1 over x dx ln x from 3 to 6. So plugging in 6, we get ln 6. Plugging in 3, we get ln 3. Using Law's logarithms, that's ln of 6 over 3, which is ln of 2. Let's find the area under the cosine curve from 0 to b, where b goes from 0 to pi over 2. So we're going to let f of x be cosine. Then an antiderivative is sine. Notice we do not need the minus because we're going backwards. When we take the derivative of sine, we get cosine without the minus. So the derivative of cosine is minus sine, but the antiderivative is just sine. Our area then becomes the integral from 0 to b of cosine x dx, which is sine x from 0 to b, which is sine b minus sine 0, but sine of 0 is 0, so we just get sine b. This is actually kind of cool because if you were to graph this, let's say from 0 to pi over 2. So here's y equals cosine x, here's 1, here's 0. That means that if I stop at pi over 2, if I make that b, then the area from 0 to pi over 2 underneath the graph of cosine is just 1. So this area over here is exactly 1. So that's really cool, and not the easiest thing to prove without calculus. Let's see what's wrong with this calculation. Well, we've got the integral of 1 over x squared dx. So that's x to the minus 2. So an antiderivative is definitely x to the minus 1 over minus 1, so that's good. We evaluate from minus 1 to 3, so that's good. Plugging in 3, we get minus 1/3. Yes, because when you plug in 3, it becomes 1/3 with the minus 1 exponent. Then minus 1 is 1, minus 1/3 minus 1 is minus 4/3. So everything looks good, except that there's a problem here. 1 over x squared is a positive function. Negative 4/3 is negative. That shouldn't be possible. If we have a positive function and we look at the area underneath the curve, we expect that area to be positive. So immediately that's an issue. F of x is equal to 1 over x squared is a positive function, but negative 4/3 is a negative answer. So what went wrong here? Well, you weren't allowed to apply the fundamental theorem of calculus. You were never allowed to get to this point because 1 over x squared is not continuous on this interval. It's not continuous on the interval -1, 3. You can see that by looking at the graph. So it's this positive function. It's just like 1 over x, it's always positive. Here's -1. Here's 3, say. Notice that there is a giant discontinuity over there. There's an infinite discontinuity at x equals 0. And that continuity messes things up so much that this integral actually doesn't exist at all. So you have to be super careful. In general, you can only apply the fundamental theorem of calculus to functions that are continuous.